Dear students, in the previous class we have discussed how to use F distribution to compare two population standard deviations. In this class, I will give a theoretical analysis of F distribution, and I will also explain the interrelationship between Z, T, F chi-square distributions. The F distribution is the distribution of the ratio of two chi-square variables. The distribution of the ratio of two chi-square variables that are independent of each other and each of which has its own degrees of freedom. For example, chi-square 1 with the k1 degrees of freedom, chi-square 2 with the k2 degrees of freedom, then chi-square 1 by k1 divided by chi-square 1 by k2 follows F distribution with the k1 and k2 degrees of freedom. k1 degrees of freedom in the numerator, k2 degrees of freedom in the denominator. And as you can see, the degrees of freedom of F is inherited from its parent distribution chi-square. In the numerator, chi-square 1, k1 degrees. In the denominator, chi-square 2, k2 degrees. And F distribution, the shape of the S distribution is, as I told you, it starts from 0. This is F. Starts from 0, only positive values because it is the ratio of two chi-square variables, and chi-square distribution is squared distribution, that is why. And as you can see, F distribution is asymmetric, not symmetric, positively skewed, right skewed. And this asymmetry is the quality obtained from chi-square distribution. Chi-square distribution is also right skewed or positively skewed. So the shape of F resembles the shape of chi-square. And as we have discussed in the context of chi-square, a chi-square distribution approaches to normal distribution as degrees of freedom increases. The same is true with respect to F also. F distribution approaches to normal distribution as the degrees of freedom increases. And F distribution is useful for testing the equality of two variances or two standard deviations. Remember this, we define chi-square as n minus 1 into S square by sigma square, and this quantity follows chi-square with n minus 1 degrees of freedom, where S square is the sample variance, sigma square is the population variance, n minus 1 is the degrees of freedom. Now, suppose that we have two independent random samples from two normally distributed populations, and we have two sample variances, S1 square and S2 square, two independently sampled populations. So we have S1 square, S2 square with the degrees of freedom n1 minus 1, n2 minus 1. Degrees of freedom n1 minus 1, n2 minus 1. Because for sample variances, degrees of freedom is there. Then let me consider a little manipulation. Now we know that chi-square 1 is n1 minus 1 into s square by sigma 1 square, and s1 square is chi square 1 into sigma 1 square by n1 minus 1. So it follows that chi square 2 is equal to n2 minus 1 into s square 2 by sigma 2 square, so that s2 square is equal to chi square 2 into sigma 2 square by sigma square 2. So we have two independent random samples from two normally distributed populations, variance from first, variance from second, with the degrees of freedom n1 minus 1 and n2 minus 1. Then consider the ratio s1 square by s2 square is equal to chi square 1 into sigma 1 square by n1 minus 1 divided by s2 square chi square 2 into sigma 2 square by n2 minus 1. This is n2 minus 1. If we assume that sigma 1 square is equal to sigma 2 square, that is h0, then this ratio becomes chi square 1 by n1 minus 1 chi square 2 by n2 minus 1. What is this ratio? This is s1 square by s2 square. So this quantity follows f with what to say? Here it is. We define it as the f. We have defined chi square f as equal to chi square 1 with k1, chi square 2 with k2, k1 and k2, n1 minus 1 and n2 minus 1. So this quantity is f with n1 minus 1, n2 minus 1. So as you can see, s1 square by s2 square is f distribution, because it is chi square 1 by n1 minus 1 over k1, chi square 2 by n2 minus 1 over k2. So we use this to test the hypothesis. Now, before concluding, let me just specify the interrelationship between these various distributions. Suppose that x is normal with the mean mu and variance sigma square. Z is x minus mu by sigma is normal with the 0 and 1. Z square is chi square with the 1 degree of freedom, and sigma z square, where z I square, I is equal to 1 to k, follows chi square with the k degree of freedom. So square of z is chi square, sigma z square is chi square with the k degree of freedom. And if z1 is standard normal, z2 is chi square with the k degree of freedom and is distributed independently of z1, that is z1 and z2 are independently distributed random variables, then the ratio z1 by root of z2 by k follows t distribution with the k degree of freedom. K degree of freedom. Z1 is standard normal, Z2 is chi square with the k degree of freedom. Now suppose that Z1 is chi square with the k1 degree of freedom, Z2 is chi square with the k2 degree of freedom, then Z1 by k1 divided by Z2 by k2 follows f with the k1 and k2 degrees of freedom. This is the interrelationship between z, x, z, chi-square, t and f. And in our analysis, we have used all these interrelationships. So remember this. If you want to implement a testing procedure based on z, t, f or chi-square, normality is required because all these distributions are related to normal distribution. If you cannot assume normality, you cannot implement any of these tests. You have to go for non-parametric procedures. Non-parametric procedures.